This is the Explorer, America's first satellite. Remember your contemporary history? October 4th, 1957, Russia launches the world's first satellite named Sputnik. America is mortified. December 5th, 1957, America launches its Vanguard. It fails to orbit. The free world wonders, has the United States been reduced to a second-rate power? The president of Caltech, Dr. DuBridge, took it calmly. He said, "I never expected to live to see the day when a leaky fuel pipe would be regarded as an international tragedy." This is the school story about teachers, students, parents. Presented as a public service by the National Education Association. Now the story of the man behind Explorer 1. Bundled all up and mysterious, this is the thing that projects man into space. It is an Explorer satellite launcher. Unbundled, it is still mysterious because of the complexity of 20th century science. Granddad never heard of a spin balance test. He would have been lost in this maze of electronics. And yet to a present-day scientist, it all makes sense. The first stage of the Explorer is a Redstone ballistic missile engine using liquid fuel. Upper stages consist of solid propellant rocket motors, which boost the satellite into required speed for orbiting. The fourth stage actually fires the satellite into orbit, and when spent, continues in orbit with the satellite. But let's go back to January 1958. America is suffering the stigma of being a satelliteless world power. The Vanguard has failed. Now the Explorer, the Army's entry, is ready to try. The weather is bad. High-velocity winds at 40,000 feet. Launching time is postponed a day and then another day. Finally, on January 31st, the upper-level winds diminish to 20 knots. The firing party goes into action. Step by step, circuits and recording instruments are checked out. Outside in the launching area, other technicians groom the huge bird for its plunge upward, fueling with powerful liquid oxygen. On the Cape, an air of cautious optimism prevails. The countdown is on schedule. What will the outcome be?
Finished fuel loading. Take a weight reading. Okay. Check the utility room fuel vapors and notify the blockhouse when we're clear to start generators. Control voltage on. Gyros on. Gyro erection on.
Regulator off. Jerry, want to turn the recorders on? Want to turn the recorder on and everything? Roger. Okay, we'll start now. Okay, Jerry.
Check the lock loading has been completed.
Regulator off.
Roger.
Jerry, want to turn the recorders on? Want to turn the recorder on and everything? Roger. Okay, we'll start now.
Connect assembly to igniters. Okay, tie down the lead.
Regulator off.
Roger, and install your protective tab. Okay?
If Explorer 1 orbits tonight, America will have begun the conquest of space. A flight beyond the confines of gravity would be a triumph for America's system of education. 15 of the key 16 scientists who developed this, America's first satellite, were products of our public schools. Some were military men, like General Medeiros, here supervising the launching of Explorer 1. But others were scientists, mathematicians, physicists, teachers. Now, as we watch this historic launching of America's first satellite, let us think of a man who is absent. He is DuBridge, one of the men behind Explorer 1. Dr. DuBridge is president of the California Institute of Technology and headed the Caltech Jet Propulsion Laboratory, which developed the first U.S. satellite. And in a few moments, we'll dig a little deeper and think of the man behind Explorer 1. His name is Smith, Dr. O.H. Smith. You've probably never heard of him. Dr. Smith is a farm boy who grew up to teach physics at a small college in Iowa, and yet he played a significant part in these events that we're watching tonight.
There's something dropping down on the jet vane instantaneously here.
Oh! Telemeter indicates the jet vane 2 is deflected. What do you want to do? Look in it. Okay, resume count.
Okay, shall we go ahead, Jim? It looks like you're here.
30 seconds. Recording's on. 25 seconds.
Regulator off.
20 seconds. On to truck package. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Firing command. Fuel tank pressurized.
10:48 hours, Eastern Standard Time. January 31st, 1958. For another 2 hours, they would sweat it out. At the Cape, in Huntsville, and in Washington. Waiting for the tiny satellite to race around the Earth and confirm the fact that Explorer 1 was in orbit.
Now meet Dr. Lee DuBridge. We call him the man behind Explorer 1. Actually, there are thousands, each playing his own part. Dr. DuBridge is president of a university, Caltech, head of a jet propulsion laboratory, renowned physicist, famous for his work in radar development during World War II, and himself a product of American public school systems. His academic achievements: A.B., Cornell College, Mount Vernon, Iowa, 1922, Ph.D., University of Wisconsin, 1926, and 16 honorary degrees from various colleges and universities. But one honor tops them all. Dr. DuBridge has been awarded the Golden Key by 8 national educational organizations in cooperation with American industry for his significant contributions to the national welfare. But now to another campus over 2,000 miles away and another Golden Key. The man who is wearing it is Dr. Orrin H. Smith, now Professor Emeritus of Physics at DePauw University at Greencastle, Indiana. It was almost 40 years ago when Lee DuBridge, then a student at Cornell College, Iowa, wandered into the classroom of physics teacher O.H. Smith. A miraculous thing happened. Lee DuBridge became enchanted with physics, and a career was born. It is now 40 years later, and Dr. Smith has been teaching for half a century. He still invites his wife to sit in on occasional classes to see if he's getting it across to the students. He was personally chosen by Dr. DuBridge to share honors with him as co-recipient of the Golden Key Award. Dr. DuBridge explains why. He says, "When I enrolled in college, I had only the vaguest idea of what kind of a career I wished to prepare for. Professor Smith helped me discover physics. It was an enthralling experience." This, the building where Dr. Smith taught physics for so many years, intriguing thousands of students with careers in science. But now it's reunion time, the moment when 2 winners of the Golden Key will meet at Caltech and talk about old times. There will be reminiscences of the evening when Lee DuBridge met the girl who was to become Mrs. DuBridge in the Smith living room. This is the campus of the California Institute of Technology in the Pasadena foothills. Here, many of the nation's top scientists are stimulated in an atmosphere of pure science. This is a Synchrotron, one of the gadgets that a university needs these days if it is to conduct nuclear research. Now, Caltech President DuBridge takes physics professor O.H. Smith on a special guided tour.
Well, here we are on top of the synchrotron. As you remember, a synchrotron is a device for accelerating electrons. The electrons are injected through the green tank over there at an energy of about 1,000,000 volts. They're then accelerated around through this path here and go around about 50 million times, and eventually they hit a target over there. And when the electrons hit a target, they have an energy of about 1 billion to 1.25 billion electron volts.
Yes. Well, you remember that figure that was in, I guess, one of the modern physics texts where the bulbs on one side,
Yes.
the exit side, was greater than that on the...
That's right. And when the electrons hit the target, most of the X-rays go forward. So that down through that side of the room, there's a beam, a narrow beam of 1 billion-volt X-rays. And then down there, they use those for all sorts of nuclear experiments.
And that's actually a momentum of a photon, isn't it?
That's right. The energy of the electron at 1 billion volts is converted into the energy, h nu, of a photon, which goes downstream. First time I ever saw an X-ray machine was in our laboratory when I was a junior. Do you remember giving me that little laboratory X-ray tube that you had there, and I was supposed to make some measurements of the ionization? That was my first introduction to
and you were measuring
to
the ionization
X-rays.
in the chamber.
Yes.
What'd you do? Put a potential across it? I kind of forgot.
A potential across the chamber and a galvanometer across it. I almost ruined a good galvanometer. I remember that. Here, of course, the electrons have to be accelerated by many, many individual impulses. Every time they go around this circle, they get an extra impulse of energy. And they travel around this whole big machine here, a total distance of about 40,000 miles before they come up to the 1 billion volts at which they hit the target.
And still they stay in that little tube.
Yeah, inside here is just a little tube so big around.
Well,
that takes pretty good design, as you see, and pretty good
Back in
accuracy.
those days, we'd have said that was impossible. It couldn't be done.
It couldn't have been done then.
No, it couldn't have been done then. This is a very expensive and a very beautiful setup, and the theory of it goes wonderfully well. I suppose the public will wonder what's going to come out of it. Do they let students work on this?
Oh, yes. Yes. As a matter of fact, a great deal of the work here is done by graduate students working in close collaboration with their teachers. This is a teaching laboratory, you might say, where graduate students learn about the techniques of nuclear physics, and they'll go on into other universities or into industry and carry the knowledge they've gained here there. Nuclear physics is an important preparation for physicists these days.
Yes.
You know, so we have many graduate students who are working on this machine every year.
And someday this will be a key to some very important progress technologically, maybe.
Maybe.
And then the public will forget that it started out as a useless sort of a plaything.
Yes, I'm sure people think that it is a useless plaything now, and when you're doing basic research, it's hard to foresee the practical applications. But already the knowledge gained with a machine of this sort has led to quite a lot of better, deeper understanding of the nature of nuclear forces. And since these are the most important forces in the universe, I think it's important to understand them and to give understanding to the students.
Well, they're the seeds from which more advanced things and more technology is to come in the future.
That's right. You've already seen some of your own former students here, or graduate students here now, so you've seen the next stage in their educational
Well, when I think
experience.
of all the work that you and Torrey and the rest of them have done, I feel that I've had my fingers to a slight extent in a good deal of work.
Hello, H. Here we are in the low temperature laboratory. This laboratory is under the direction of Professor John Pelham, our expert in the low temperature field. This is just one of the experiments that he's been carrying on recently. This silver flask here has on the outside of it a layer of liquid nitrogen, which assists in the cooling. Then inside that is a column of liquid helium. Now liquid helium normally at atmospheric pressure boils at about 4 degrees above zero, absolute. But they pump off the helium through that pipe off to a pump in the other room. And so the liquid helium is boiling under very low pressure. And this reduces the temperature down to about 1 degree, absolute. Well, then the liquid helium, in turn, cools a little a piece of a paramagnetic salt, which is down there between the poles of the magnet. And if that is cooled with the magnetic field on, and then the magnetic field is taken off, so it's demagnetized, that cools the salt down to 5,000th of a degree above absolute zero. 5,000th of a degree. Now, at 5,000th of a degree in a magnetic field, the individual nuclei of the salt become lined up. And they put in a little radioactive material, some radioactive cobalt. And so the cobalt nuclei get lined up in the magnetic field. And they stay lined up as long as the temperature is down at 5,000th of a degree.
Even when you take them out of the field.
That's right. And now they can find out whether these radioactive nuclei emit their gamma rays in the forward or in the sideways direction. Let's go over here to this counter, and I'll show you how he does it. He has a counter set over there, and he brings this demagnetized but still very cold salt material in here and places it in front of this array of counters. Now these nuclei are lined up, and he can count with these scintillation counters in which direction the gamma rays are coming out. And he finds that if the nuclei are lined up this way, that more gamma rays come out sideways than in the forward and aft direction of the magnetic dipole of the nucleus itself. So this is one of the exciting things that they are able to do now with this extremely low temperature technique, getting down to temperatures of a few thousand.
Well, now that you're down to 5,000s, is absolute zero minus 273, or not exactly, probably?
Well, it's 273 plus a fraction. But it's easier to just take absolute zero and measure everything from there. And then you don't have to worry about exactly how far below the centigrade zero the absolute zero is. Well, that pumping line then leads over to this pumping equipment over here. We pass through some rather elaborate glassware that's used in connection with all of these various experiments and get over here to the pumping line. And here's where the helium is pumped out through valves and pipes and so on into pumps into the next room. And it's this pumping line that reduces the liquid helium's pressure to the point where the liquid helium itself cools off to about 1 degree absolute.
Well, then you save the helium for
and you save the helium and liquefy it again. Let's go over now to another laboratory where we'll be dealing with high temperatures instead of low temperatures.
Good.
Over on the next level.
Good.
This is a X-ray diffraction camera for high temperature metallurgy, OH, believe it or not. All of this equipment is in order to get good X-ray diffraction pictures from metal samples at quite high temperature. You see, in modern metallurgy, it's terribly important to be able to find out what happens to materials of all kinds at very high temperatures, up close to the melting point. And it's never been possible to do this very satisfactorily before until one has a complete outfit that can be evacuated to prevent corrosion and everything else, and that the temperature can be brought right up close to the melting point of the sample you're studying. And so here the X-ray machine and all those crystals and camera and counters and everything are all inside of this great big tank, which is then evacuated to a very high vacuum. And the sample then can be brought up to a very high temperature and study precisely what happens to it as the temperature is lifted almost to the melting point.
Sure.
This, of course, is pretty important in modern metallurgy, and especially in modern aeronautics and aircraft design, satellite and missile design, where very high temperatures are likely to be involved, and we need to know something about the properties of these metals at high temperatures. So that's the reason for this rather elaborate outfit, which has had a wonderful history of good results in this field.
That's a very impressive thing.
The man who is in charge of this is Professor Paul DePauw. He's interested also in the jet propulsion field and in satellites and rockets, and has done a good deal of work up at the Jet Propulsion Laboratory.
Well, speaking of satellites, this is a very interesting approach to it. Didn't I see a satellite over here? Would you show me a little about that?
Yes, this is a model of the first Explorer satellite. Let's go over and take a look at it. Well, this is a model of the Explorer satellite series. The first one was fired in January 1958. This is the payload only, the nose cone, what contains the instruments. This black and white striping is quite important. The white stripes reflect the sunlight, and the black stripes absorb it. And if you have the proper ratio of area, then you can keep the temperature inside the satellite at the right value.
I remember Picard had found out some things about that.
That's right. All of these satellites have to be properly balanced for radiation to keep the temperature right. This worked pretty well. The temperature stayed just about where they wanted it. Now, here you can see the cutaway view of it showing the instruments inside. At the top, there's a radio transmitter with its batteries. Then there is a Geiger counter, which was intended to count cosmic rays or any other radiation to be found in space. And at the bottom, there's a second transmitter, a low-power transmitter, which lasted several weeks longer than the high-power transmitter. The low-power transmitter, however, was such a low power that only very special receivers could pick it up. But it was picked up by special receivers. Now, in the later versions of this satellite, the Geiger counter information was put on a tape recorder. And then you could collect information as it circled the entire Earth. Then when it got back over Los Angeles, you could trigger it from the ground, and it would play back its entire recording it had taken in its trip around the Earth. Now, it's very curious and very fortunate that it was a Geiger counter that was carried in the Explorer satellites, the first U.S. satellites, because these Geiger counters picked up, the very first one, a radiation level way, way beyond the cosmic rays, 1,000 times more intense than the cosmic rays were known to be out there. And the puzzle is what caused this? It paralyzed the counter, so the counter simply had stopped working. And this was quite a mystery at first until somebody said, well, it's simply because the radiation level is so high that the counter is paralyzed. So in the second and third and later satellites, other counters were put in and circuits were put in to avoid the paralysis. And then it was found that, sure enough, as you go up from the Earth, the radiation begins to increase rapidly at about 500 miles, increases to a very high peak at 1,000 miles, then falls off again, and then starts climbing way up again, and at about 8 to 10,000 miles, it's at another high peak. And this apparently is a double-banded cloud of particles trapped in the Earth's magnetic field between 500 and 12,000 miles off the surface of the Earth. Whether these electrons and protons, or whatever they are, come from the sun or from outer space or from the upper parts of the Earth's atmosphere, we just don't know. Since you're from Iowa, you'll be interested to know that the cosmic ray circuit was designed by Dr. James A. Van Allen of the State University of Iowa at Iowa City. The Pioneer satellite is, of course, a little bit differently designed from this, and this was intended to go to still higher elevations and to get still more complete information about this radiation band.
Well, that thing has attracted a lot of attention and made it appear to parents, at least, the amount of education that students nowadays should have.
I think maybe one of the most important results of the satellite program of the U.S. so far is that it's impelled the American people to take a greater interest in their schools.
Yes.
To improve their instruction, to get the very best teachers available, to teach their students, to provide them with the kind of equipment and the time, and especially the intellectual stimulus, so that they will pay
in order
attention.
to get up this far.
They'll pay attention to the real solid subjects in their school career.
Yes.
So I think American schools are going to be better off, and high school and grade school kids will get a better education in coming years, partly as a result of this stimulation. You never can tell what's going to be the result of a scientific experiment.
No, and you can't tell what the reaction's going to be on the students.
Enough of the new things of physics. Now let's reminisce a bit, personally perhaps. President DuBridge and his former professor of physics sit on the Caltech campus and think of the good old days back at Cornell College, Iowa.
Physics has changed a little bit in the last 37 or 8 years since...
and this is a different kind of a campus from what old Cornell's campus was.
Yes, and it's different from what it was in 1921. You were here before, I believe, in 19...
Yes, I was here in 1923.
On your way to...
I think down in that building there.
Yes, well, this was all open ground then. There were no buildings here at all. The other end of the campus was in an orange grove. Well, it's
I remember that building.
to have a chance to have a reunion with you, and I'm so glad your wife is here.
I brought along this old
the college annual of
college
1922.
annual, yeah. You remember that young lady right there?
Yes. That's Mrs. DuBridge now.
Yes.
I would hardly recognize you here. This picture of you looks really as though it were taken a long, long time ago.
Yes, well, I don't have as many gray hairs there as I do now.
Yeah.
I required a few of those.
I tried to destroy this picture of me, which is pretty bad, but I was not able to.
I like
to
it.
destroy it.
I like that picture. Yeah.
Well, I'm afraid that's the way I looked at the age of, what was it, 19 or 20?
About 20, I guess.
Yes.
Yeah. Well, this campus isn't tipped up quite so much as the Cornell campus.
Well,
You get a
we
different
had
kind of...
some long, cold walks up the hill through the snow there in the winter time.
You remember how the chapel looked on a sudden change in temperature when it would be covered with frost? Let's see, Lee, you were assistant about, 2 years or 3?
2 years.
2 years.
I mean,
Junior and senior year.
Well, that's right. While I was a sophomore, I took the first course in physics, and about the spring of that year, you said, why don't you take the advanced course in physics and serve as a laboratory assistant? That's where my career, if you want to call it that, in physics took off.
Well, that was an awfully good start.
How did you know I wanted to be a laboratory assistant?
Well, maybe the problem was that I wanted a laboratory assistant.
Anybody would do it.
I picked out the most likely and the best looking one.
Yeah.
The most likely and the best looking. Dr. Smith's analysis of why he chose Lee DuBridge to be his lab assistant. He turned learning into adventure. Dr. DuBridge's analysis of why he selected a career in physics. Dr. DuBridge, one of America's top scientists, president of an outstanding American university, recalls how O.H. Smith used to conduct class. He says, he often deliberately posed a problem backwards, as if holding out a pair of scissors with the points toward you. You had to learn to grasp it from every angle. He squeezed knowledge from every experiment like juice from a grapefruit. At the end of each hour, he left us with a question, a paradox to be resolved next time, like a continued story in a magazine. With O.H., physics was an intimate part of everyday life, explaining the simplest things and illuminating them. He would take up a piece of chalk saying, let's work a problem together. Writing a seemingly simple equation, he asked our help. As we spoke up, he purposely made mistakes, stirred up arguments over elementary laws of physics, pursued wrong suggestions to the end of a blind alley, until half of the class was completely bewildered and the other half roaring with laughter. Just as the youngsters of 100 years ago were excited about the pushing back of America's western frontiers, so the young people of today can reap equally great rewards from hearing about the frontiers of science. Fortunate indeed are those of us who have been introduced to the great adventures of science through the genius and human understanding of a truly great teacher. There's no substitute for a good teacher. Remember, your child spends 900 hours a year in the classroom, and you want those hours spent under the guidance of the best prepared, most alert teachers that your community can provide. But you have a responsibility too. Children go right on learning outside of the classroom, and this time you are the teacher. You have a golden opportunity to build on what he learns in school, to help him stretch his learning wings. You can work along with his teachers to spark your child's curiosity, energy, and enthusiasm for knowledge. To help you do this, the National Education Association has prepared a leaflet especially for parents. It's called 35 Ways to Help Your Child Learn. Write for your copy today to National Education Association, Washington, 6, D.C.